is that. Good morning, everybody. Welcome back. Thank you. And welcome back to Calc 1. Plan for today is we're going to finish up Standard 9 by doing a few example problems, and then we're going to move on to Standard 10, in which we're going to start talking about differentiability. How can we tell if a function is differentiable or not, based on some properties of the function, including looking at its graph. I've got my usual office hours over the next few days, today and Wednesday at 11 and 2, tomorrow at 11 and at 1. And as far as homework goes, we are going to have a quiz Wednesday on Standard 9. And also don't forget, you have a web work due on Wednesday. My goodness. Squeaky. Any questions or comments before we get started for today? So, I met with some of your parents over the weekend. That was delightful. Apparently, a couple of you have been telling them that you've never seen my face. There's a reason for that. It's because I don't have a face. I just have a black void underneath this mask. Alternatively, now you know. Okay, so we left off last time. We had talked about how to find derivatives of exponential and logarithmic functions. Specifically, we showed that the derivative of a to the x is just going to be a to the x times the natural log of a, where natural log is log base e of a. And that the derivative of the logarithm, log base a of x, is just going to be 1 divided by x times natural log of a. And as a consequence of those, if we look at a equals e specifically, the e is that 2.71 magic number where e to the x is its own derivative. If we were to plug in e here, in either case, we get that the derivative of e to the x is in fact just e to the x, since natural log of e is 1, and the derivative of the natural log of x is going to be 1 over x. So what I thought we could do to start class off today is to just take a few minutes and look at a few practice problems regarding how we can kind of use all these different derivatives that we found so far. Probably throw in here into the mix what we found earlier last week, which is that the derivative of sine is cosine, and that the derivative of cosine is negative sine. So what I would like for you to do is, if you go in your packets to the last couple of pages where it says, now let's differentiate the following functions at the top, I'm going to give you six sample problems on this page and the next page. So what I'd like for you to do to start things off is working with your neighbors, as always talking to the people sitting around you. See if you can find how to take derivatives of these 6 functions using what we've talked about over the last week, as well as our earlier rules like chain rule, product rule, power rule, etc. Go ahead and take a few minutes and see what you find. Go ahead and write these up on the board too while you're looking at it. Bless you. As always, if you feel like you're not sure about something, feel free to flag me down. And also, I encourage you to talk to your neighbors, see if they got the same answers that you did. Sounds like you want to do a little bit of implicit differentiation. You could do that. So basically, replace, so this would be log base 3 of y equals cosine of t. That's good. I think you need, I don't think you should use the same variable x in both cases, because this one is sort of like your y, whereas t is behaving like your x here. Yeah, that would certainly be one way that you could approach that one, to do it implicitly. It's not what I had in mind, but it should work out.
X squared divided by x, or negative x.
And if you do this chain rule. Like when there's like the sine 1 over x, you just chain rule. Yeah. What'd you get for K?
Please don't try and simplify it.
K of 4.
Yeah,
I was gonna stop.
I was going to say, for the fifth one, m of x, the derivative is a bit messy. Don't worry about trying to simplify it.
Check out the first one.
You get the right answer for this one.
What's that? No, I did.
Oh.
I'm at the second one.
If you use product rule there. Amateurs.
Yeah. Oh, don't get me started on you.
Hey, I'm only bad at standard 8. That's
They say you both are doing fine.
That's what I do.
Did use product rule. So you
I just want to write out x.
yeah.
I have more mastery. So I have more mastery.
Where?
I have 2. I have 2 in every other.
You don't?
Yes, I do.
You did not.
Yes, I do.
So did you give it
Like insights toward the head.
Very.
Wait, what about this one?
Oh man, I don't know if I did this one right.
How do you even know how to do that?
Because you can simplify log on natural log less too, because the log thing. Use the log thing. Change. That's the only good thing about it.
Sure.
Joshua will right now.
Sounds good to me. Sounds like that. I know.
Joshua, nice.
Sine x plus 5 to
Yes, although the derivative of the inside would just end up being 1, so I just end up differentiating that side on that. So technically, yes, to differentiate sine of x plus 5, you would need to.
Avery. That's 5.
That's the only one.
Oh, I'm doing this. Yeah.
I don't know.
Sine of x plus 5. No, the derivative
No,
of that.
y'all suffering over here.
Okay, when you have this, do you have to take the chain rule, or can you just take?
Just take the derivative of sine of x plus 5. Technically, you would need to use the chain rule, but also in that one, the derivative of the inside turns out to be 1, so sine of x plus 5 will be separated.
Dummy.
But technically, yes, you need to use the chain rule on that one.
Oh my.
If it was something like sine of 2x plus 5, then the chain rule wouldn't matter anymore.
So then you got your factors here.
Y'all doing it right up here now?
No.
No!
He's being
I just told you.
That quick picking on her.
I didn't know. She goes, would this be right? I was like, think about it. That position. What's that supposed to mean? I was like, that's not right.
Oh, yeah, that's exactly how you said it.
Alright, come on, let's be polite.
I was kidding.
I think, but.
You always, if it's in the X, you always have to use the chain. You always have to use the chain. Always.
I don't understand, like, what would be the outside, what would be the inside derivative? So the sine of x is the outside. X was not x inside.
So what's the inside? Things and what's outside? It's not that hard. 60.
I never have to take that one.
The X fiber outside. It's not. It'll just be one.
Okay, but then we have actually, there's this indication.
Wait. See, no matter what, derivative of x plus 5 is 1. So you don't need to worry about it.
Oh,
The derivative of x plus 5 is 1. So you don't even need to worry about doing that chain rule. Because it's going to equal 1.
We can do the chain rule.
That's why you have the cosine x plus 5.
Where did that come
You have to chain rule like
I didn't change.
Let's take another minute or two, and then we're going to come back together to talk about a couple of these.
The chances of me simplifying this are exactly none.
Okay.
So we already graduated. So it's like, oh.
And that's why I never get mine straight.
I don't.
Based on principle, I refuse to simplify. Oh my goodness.
You didn't simplify that, did you, Toby?
Nope, I never simplify. He said he didn't even realize.
Just chill out.
Oh, we don't know this right.
I'm getting there.
Thanks.
You just did it.
You just gave me so much abilities that
It's okay.
I just know for
Sling
sure.
that. How do I take it?
Never gonna get another problem.
Alrighty, let's come back together as a class and talk about a couple of these. So, something I don't want to go through all 6 of these in the interest of time, but I'd like to talk about 2 of these. However, instead of me picking out the 2 I'd like to talk about, let's let you all decide.
K of X.
Yeah, that one.
So, hold your horses. First of all, I realized that I've made a terrible error, which is that I forgot to do the joke of the day. So, a mathematician decides one day that he is sick of math. That's the joke of the day. That would never happen. No. Mathematician decides he's sick of math, and he goes to the local fire chief and says he wants to be a fireman. Fire chief says to him, you seem like a good guy. I'd be glad to hire you. First, I have to give you a little test. Chief takes the mathematician to the alley behind the fire department, which contains a dumpster, a spigot, and a hose. Chief says, all right, suppose you walk into the alley and the dumpster's on fire. What do you do? Mathematician thinks about it for a minute and says, well, I think I would connect the hose to the spigot, turn the water on, and use the hose to put out the fire. Fire chief says, oh, that's great, perfect. Now, what would you do if you're walking down the alley and you see that the dumpster is not on fire? Mathematician has to think about that one a bit longer. And finally he says, well, the first thing I would do is I would start by lighting the dumpster on fire. Chief says, what? That's terrible. Why would you light the dumpster on fire? Mathematician replies, well, that way I reduce the problem to one I've already solved. Okay, so I'd like to do kind of a little informal vote on which 2 problems you would like to see. Let's go ahead and pick out your favorite problem or 2 from this list, one that you would like to see worked out as a class. And we'll do the top 2. We'd like to see f of x, b of t, h of x, 4, 5, 6, k of x, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, m of x, 1, 2, 3, 4, and z of t, 1, 2, 3, 4, 5, 6. All right, we're doing these 2. So let's take a look at, I get to pick 2 right on top of each other. I'll rewrite m of x when we get to it. So let's take a look at k of x here. The natural log of 5 to the x. So to me, it looks like we have 2 different things going on here. The first thing that we're doing is we're taking 5 to the x as sort of an inside function. And then once we take 5 to the x, we take the natural log of whatever that is. So how could we go about, differentiating this? To me, it looks like we have sort of an inside and outside function going on here. Avery?
You need to use the chain rule.
Okay, we need to use the chain rule. So if this is our kind of outer function, and this is our inner function, what would we get if we tried to differentiate this using the chain rule? Rachel?
For the outer function, well, it would be L of x, and then the derivative is 1 over x.
Yeah, so our derivative of our outer function, which is natural log of x, is going to be 1 over x. How about the derivative of our inner function? 5 to the x times natural log of 5. Where our g of x is natural log of x, our h of x here is going to be 5 to the x. So if we want to differentiate using the chain rule, as Avery suggested, we're going to need to take g prime of h of x, meaning we look at our g prime of x formula and replace all of our x's with h of x. And finally, we'll multiply that by whatever h prime of x turns out. So if we plug that into this expression, what are we going to find? When?
You're gonna get 1 over 5 to the x times 5 to the x times ln of 5, which the 5 to the x's in the numerator and denominator will cancel.
Okay, before we do that,
Oh, sorry.
no, I totally agree. I just want to make sure everybody kind of gets to this part first. So where did 1 over 5 to the x come from?
That's your g prime of h of x. So this your g prime is 1 over x. And then you input h of x for x, g prime of x, so it'll be 1 over 5 to the x.
Okay, so to take your g prime of h of x, you replace all your x's in g prime of x with 5 to the x to get 1 over 5 to the x. I like it. So here that's differentiating the outside, differentiating natural log of thing is 1 over thing. And then if we differentiate the inside component, the 5 to the x, that'll give us a 5 to the x natural log of 5. And then what did you say will simplify by?
The 5 to the x's will cancel in the numerator and denominator.
Hey, how about that? Do the old swoosh swoosh. So what'll we be left with?
ln of 5.
Hey, it's a constant. Turns out the derivative is just going to be natural log of 5. Because we have these 5 to the x terms, 1 over 5 to the x, and 5 to the x will combine to give us 5 to the x over 5 to the x, which just cancels out. And so we're only left with this natural log of 5 term. Yes, sir?
Would that be the case for anything natural log a to the x? It'd be natural log of a. It'd be just the derivative.
That has a conjecture. That's your conjecture? Well, let's see if we can find that out. I think the answer would be yes, because there's nothing really that special about 5. If you just replaced 5 with a here, where a is any positive number not equal to 1, I think this is going to check out here. So yeah, I think so. Yeah, it's a good observation. Turns out natural log of an exponential will always kind of simplify out to a constant like this, just the natural log of whatever your base is. Rachel, did you have a question?
I was gonna say the same thing.
Yeah, the same one. Any questions or comments about this? So sort of using what we've talked about earlier in this standard with how you differentiate logs and exponentials, as well as combining with the chain rule. Okay, and then the other one that I think got the most votes was this m of x. Here we got m of x equals sine of x plus 5 divided by e to the 5x cubed minus 5 eq. So right off the bat, what rule do you think we're going to need to use in order to help us differentiate this one?
Quotient rule.
Quotient rule, because we have something divided by something else. I'm on board with that. So let's try and use the quotient rule in this thing. It's going to tell us we'll get low, 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 d high, eq. What's the derivative of sine of x plus 5 going to be? Okay. with your hand.
Oh, cosine x plus 5.
Okay, Mackenzie, is that what you're gonna say? I think we can differentiate sine to give us cosine, and then technically we need to multiply by the derivative of the inside, but the derivative of x plus 5 is just gonna be 1. So using the chain rule on this, yes, Danielle, is just going to leave us with cosine of x plus 5. Minus d low. Yeah, Zooks, we need d low now. Derivative of e to the 5x cubed minus 5.
Wouldn't it just be e to the 5x cubed minus 5?
Just another copy of e to the 5x cubed minus 5. Derivative of e to the x is e to the x. So should the derivative of e to the 5x cubed minus 5 be e to the 5x cubed minus 5?
You have to change the exponent as well.
Oh my gosh, we have to chain rule here. We have an outer function, which is e to the x, and an inner function, which is 5x cubed minus 5. Gosh, you are looking very incredulous right now.
Weird.
Quite. So the derivative of e to the 5x cubed minus 5, if we differentiate the outside piece, the e to the x, we'll still get back that e to the 5x cubed minus 5 piece that we started with. That's like our g prime of h of x here. But we also need to multiply by the derivative of the inside, the 5x cubed minus 5. Which, Mackenzie, what's the derivative of 5x cubed minus 5 going to give us?
15x squared.
I think so. So we'll have an e to the 5x cubed minus 5 times 15x squared from using the chain rule here. And technically, we needed the chain rule to get, we did need the chain rule, cough, cough, to get that the derivative of sine of x plus 5 is cosine of x plus 5. Yes?
Can you show the chain rule for that?
Yeah, for the e to the 5x cubed minus 5?
Yeah.
Let's do it. So this is just as an aside, if we were to write out f of x equals e to the 5x cubed minus 5, what would our g of x and h of x be? That would make it so that like g of h of x is equal to this function. In other words, what's our inner function and our outer function going to be? Okay?
G would be e to the x,
Okay, and h?
5x cubed minus 5.
Cool. So if we differentiate each of these separately out to the side, our g prime of x, I think it's just going to be e to the x, because e to the x is its own derivative. As Mackenzie pointed out, h prime of x is going to give us 15x squared. And so when we take our f prime of x, which according to the chain rule should be g prime of h of x times h prime of x, what would our g prime of h of x end up looking like? So in other words, if we take our g prime of x and replace the x here with whatever h of x is.
E to the 5x to the third minus 5.
Yeah, just taking this x and we replace it with 5x cubed minus 5, and that's how we get our e to the 5x cubed minus 5. And then if we multiply by h prime of x, that'll give us our times 15x squared.
But like, I guess the one thing I'm confused on is like, that's the 5x cubed minus 5, that's in an exponent. So can you just bring it down like it's a normal number, or?
Sure.
Oh, okay.
Well, the fact that we're just bringing it down and multiplying by 15x squared like this, that's just as a result of using the chain rule, which always says differentiate the outside function, leaving the inside bit alone, and then always multiply by the derivative of the inside function. And the chain rule, it don't care what type of well, it sort of cares, but we'll see in standard 10 when it matters. Chain rule doesn't generally care about what types of functions you're using with it, whether it's exponential or trig or power functions or quotient things. Chain rule always is going to work the same way. The only thing that's kind of new as of the standard 9 stuff is how we would differentiate each one of these individual pieces, the g of x and the h of x individually. Does that answer your question?
Thank you.
This is only coming from the chain rule. We wouldn't otherwise differentiate like we would another function. So the moral of the story is if we were to differentiate something like 2 to the x, we wouldn't use the power rule. The power rule only gets used when you have x to a power of some constant value. When you have a constant number raised to some power involving x's, you would not use the power rule, though. You have questions or comments? All right, I didn't include this one in the packet, but I think you all are ready for it. How would we differentiate this function? J of x equals x to the power of x. So first of all, can we use the power rule on this?
No.
Rachel?
No, you can't use it
Why not?
because it has x in the thing.
Because we have an exponent of x and not a constant? Yeah, power rule only works if we have x to the power of a constant, which we don't have here. How about our exponential rule? Derivative of a to the x is a to the x natural log of a. Can we use that on this? Helen?
Because a is a constant. And
Ah.
x isn't.
We don't have constant to the x power, we have an x to the x power. So we can't use either of the rules we've seen. We can't use either the power rule or the exponential derivative rule on this one. Okay.
Can you just not do it?
I mean, oh snap, you just showed me. Yeah, you could not do it, but that's not why we're here.
Well, not do it because you don't want to. Not.
Oh, because it's impossible?
Yes.
No, it's not that either. We just have to be sneaky about it. I'm going to rewrite it as e to the power of natural log of x to the x. Because if you remember, we said last week that taking e to the power of thing and natural log of thing are inverses of each other. They cancel each other out. So in general, e to the natural log of x should just give us x. And the same is true if we were to take e to the natural log of x to the x instead. Dr. Gerstle, why did you do this? You just took something scary and made it scarier. Check this out. Now we can use one of our exponent properties and pull our exponent inside the logarithm out in front, using the property of exponents that said that natural log of a to the b power is b times natural log of a. Meaning inside of a logarithm, exponents can be pulled out in front as constant multiples. And now, that that's something I think we know how to differentiate, theoretically. So e to the power of x natural log of x. Take this with me. I think if we use the chain rule on this, this is something that we should be able to differentiate. So how could we write this as some g of x composed with h of x, where h of x is our inner function and g of x is our outer function? Rachel?
G of x would be e to the x, and h of x would be x ln of x.
Like that? When? Does that sound good to you? Sounds good to me. Yeah, because if we took g of h of x, if we replace this x with h of x, we would get our original function. I'll do the hard one. G prime of x is e to the x. What would our h prime of x look like in this case? Yeah.
You probably have to chain rule it.
Probably have to chain rule it?
Yeah.
What's your inner and what's your outer?
Oh, sorry, product rule. Wait a minute.
Oh, product rule. Yeah, I think product rule is going to be a good idea here because we have an x times natural log of x. We're kind of multiplying two different x pieces together. So, Sam, you want to give it a try? How would we use the product rule here?
Yeah, it would be x times 1 over x
First times derivative of second,
plus ln x times 1.
plus derivative of first times second will give us 1 times natural log of x. Can we simplify this?
Yeah, you gotta swoosh swoosh.
You'll swoosh swoosh. And what'll that leave us with in our first term?
Oh, just 1.
Yeah, I think we'll get a 1 plus natural log of x once we combine the x times 1 over x. This x and the 1 over x will cancel out to just give us a factor of 1. All right, we're finally ready to do our j prime of x here. Because we'll need to take g prime of h of x multiplied by h prime of x. What would our g prime of h of x end up looking like?
It would just be e to the x ln x.
E to the power of x natural log x? Like that? And then multiplied by h prime of x will give us a 1 plus natural log of x. Do we have any way that we could simplify e to the power of x natural log of x? What?
X to the power of x.
X to the power of x? How the heck would you know something like that?
Well, we started j of x is equal to x to the power of x, and e to the ln of anything, they cancel each other out, so.
Ah, by our work over here then, in other words.
Yes.
Yeah, we already showed that e to the, well, we did it in reverse, but we showed that x to the x is equal to e to the x natural log of x. So I think here we could just say in reverse, we don't need to redo that work. We can just write this as x to the x times 1 plus natural log of x. And I know many of you out there are silently praying to yourself right now, Please, Dr. Gerstle, don't give us one like this on the quiz. I am not going to. But I thought this is kind of an interesting kind of side exercise. How would we differentiate something where we have both x's in our base and our exponent? And the way that you would differentiate that is via some e and natural log trickery. I think this is probably the best way to differentiate this. There's other ways we could differentiate this. If I really wanted to, we could take natural log of both sides and make this an implicit differentiation problem. But I think rewriting as e to the x natural log of x and using the chain rule is probably the simplest. So, it's going to do it for standard 9. It's probably the longest standard we've had this semester so far. Just in the sense that there's kind of a lot, that we've talked about. That's some review of exponentials, trig, logarithm functions, and then today, kind of taking what we've done last week and combining it with our friends, the chain rule, product rule, quotient rule, power rule, and some different constant multiple rules, etc., etc. So, Dr. Gerstle, it's on a quiz over such a lot of stuff. What are you likely to ask us? What I'm likely to ask you is something like what we did today. Here's here's a couple of functions, differentiate, that involve exponential, trig, differentiate. So you'll probably be prepared for a couple like this on the quiz for Wednesday. Any other questions or comments before we move on? Yes, Tom?
Well, we have to know like the properties of sine and all of that, and cosine.
Properties of sine and cosine. You should know that the derivative of sine is cosine and cosine is negative sine. Well, you have to know things like sine of x plus 2 pi is sine of x, that they're periodic of period 2 pi. It's a nice thing to know, but I'm not going to specifically ask you that on the quiz. What I'm going to ask you on the quiz is going to be about the calculus aspects of sine and cosine, not about the parts that I consider to be the review aspects of it. And no, you're also not going to have to know things like the sine of x plus y is sine of x cosine y plus blah, 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 because I can barely remember those. You're probably not going to need those. If you do, I will give you the trig sheet. So you'll have that in front of you.
Will we need to do the types of problems where you have like the unit circle to plug in that type of stuff? Do you know what I mean?
So if I were to ask you, say, something like, Danny, what's cosine of 5 pi over 3? Theoretically, I could ask you a question like, all right, let's take f of x equals sine of 5x squared plus 3. You differentiate it. Now, what is f prime of pi over 3? And then that would require you to know something like that. If I did, I would give you a copy of the unit circle. You don't have to memorize it, but you should know how to use the unit circle to evaluate something like that, where it's not explicitly written out, but you would go to the angle 5 pi over 3, take the x coordinate of that. I don't know if this could be a class about memorizing the unit circle. I want you to know how to use it, but I don't really care if you memorize all the angles and their cosines and sines. You have better things to do.
Will the solution to this pack be posted so we can check the others?
You bet. In fact, it already is. I'm surprised I put it up yesterday. I don't know why you came to class today. When?
Do we need to know the derivatives of tangent, secant, cosecant, and cotangent?
Good question. Do you need to know the derivatives of tangent, secant, cosecant, and the fourth one I forget? Cotangent? I don't think I said that. It couldn't hurt. I expect you to remember that the derivative of sine is cosine and the derivative of cosine is negative sine. Don't try and don't force yourself to have to rederive those on the quiz because that's long and hard. Once you know the derivative of sine and cosine, it's pretty quick to get the derivatives of the others if you know what you're doing using the quotient rule and or power rule / chain rule. For something like that, if you don't know it, you should be aware of how to rederive that. Especially because we didn't do cosecant and cotangent in class. Any other questions or comments? I am aware that this is a scary standard. It has all these functions in it. Like this standard right here is what separates 120 from 112. The lowercase do calculus split up over 2 semesters. Whereas we doing it all in one, and so we're doing the trig and exponential and log stuff all in one. So I'm purposely, I am aware of that. I'm purposely not gonna try and ask something too challenging on the quiz conceptually, because I know that the individual functions themselves are scary and kind of difficult to work with. That's why I wanted to go slowly through some examples in class today of how to combine everything we've talked about so far. With that in mind, congratulations, you've made it to double digits. We're starting standard 10 now. All right, I'll look at absolute value function. Probably the last function you've seen, like last kind of standard sort of function you've seen before in calculus or in pre-calc classes, other than trig, exponential, log, is absolute value. And it's one we haven't talked about yet, so I figure it was high time. Here's what the absolute value function looks like. If I were to ask you to take the absolute value of something positive, like say 4, it's your lucky day because the absolute value of a positive number is just that number again. What if I asked for the absolute value of something negative?
It's just positive.
It just ends up being the positive version of that number. And finally, how about absolute value of 0? Well,
Would not just be 0.
it wouldn't be. Despite the fact that I seem to have written something that might look closer to 6. Yeah, so basically what the absolute value function does is it takes in a number, and if that number is negative, it makes it positive. Otherwise, it just leaves that number alone. If we wanted to, we could actually write out absolute value as a piecewise function and say if x is positive or 0, absolute value just spits back out the number you plugged in. Absolute value of something positive or 0 is just that number again. Whereas if x is a negative number, make it positive. And the way you can make a negative number positive is just multiply by -1. Take negative of x. And if x is negative to start, then the negative of negative becomes positive. This would be how we could write out absolute value as a piecewise function. What's f prime of 2 going to be? Keeping in mind that at the point x equals 2, the function behaves just like the line y equals x. If I were to ask you what's the derivative of y equals x at the point 2, what would you say? I think it's going to be 1, since at y equals x, we could say, or at x equals 2, we could say that f of x behaves like y equals x, according to our piecewise function. How about at f prime of -1? -1. What's going to happen if we end up trying to differentiate that? Rachel?
Would it be -1?
Why?
Because the slope is gonna be negative since it's on the other side of the y-axis.
Quieter and quieter as you say it, but I like it. Yeah. Since at x equals -1, the absolute value function behaves just like the line y equals -x. And y equals -x has a slope of -1. Since at -1, f of x behaves like y equals -x. You all can probably guess what question I'm going to ask next.
F prime 0.
What's f prime of 0? That?
It's undefined.
Undefined? Why is that?
Since it's a piecewise, there's technically 2 derivatives. If you take it of the -x, you get a different answer. If you get x, you get a different answer. So it's undefined.
Oh my gosh! The slope coming from the left is different from the slope coming on the right?
It'd be like the limits we do, like the undefined rule. If the slope from the left isn't equal to the slope to the right, isn't equal to the actual function, you can't have a limit.
So it sounds like we originally defined the derivative to be a limit as h goes to 0 of blah, blah, blah. So it sounds like you're saying that if we were to take the limit from the left of that, if we were to take that limit and write it as a left and right-hand limit, the left and right-hand limits will be different, so the overall limit, and thus the derivative, would be undefined?
Yeah, we have to take the limit of the derivative, not the actual function, because the actual function would be okay, but if you take the limit of the derivative, you get a different answer.
Gotcha. Let's do that. I like that. That's exactly what I had planned, in fact. So what Zach has proposed is that we use the limit definition of the derivative, and don't worry, this one won't be super complicated, to actually go through and see what happens if we try and evaluate f prime of 0. Which by definition should be a limit as h goes to 0 of what? F of 0 plus h minus f of 0 all over h. And what Zach has proposed is that in order to evaluate this limit, we need to take a limit as h goes to 0 from the left and from the right, because f of x is going to behave differently to the left of 0 and to the right of 0. Let's try that. Since it was your suggestion, you want to start with the left or right side?
Left.
Okay, so if we start from the left, we're going to be taking a limit as h goes to 0 from the negative side of f of 0 plus h minus f of 0 all over h, which I think is going to be a limit as h goes to 0 from the left of whatever f of h is. F of 0. You all said earlier that f of 0 is just 0. Absolute value 0 is 0, so we can just plug that in over h. And here's the tricky part. If as h is approaching 0 from the left, meaning if we're looking at values of h that are a little bit less than 0, just a little like -0.1, -0.01, etc., how can we write what f of h is going to look like a little bit to the left of 0? Let's ask a different question next. If I were to take the absolute value of, let's say, negative 0.1, what would we get?
0.1.
And we get a positive 0.1. If we were to take the absolute value of negative 0.001, you get positive 0.001. And if h is negative, the absolute value of h is going to be what? I'll give you a hint. Use the piecewise definition. What's that one?
Sorry, I said positive. You said if h is negative, you take the absolute value of it.
I take the absolute value of h, so what would that be equal to?
Negative positive. H.
Equal to positive h? Like that? I know what you're trying to say, which is you need to take h and make it from negative to positive. So if you want to take something negative, like negative 5, what would you have to do to it to make it positive 5?
Multiplied by negative 1.
Yeah, so the absolute value of h is going to turn out to be negative h in the case where h is a negative number. If h is something that's less than 0, its absolute value is going to be equal to the negative of h. And so if we look at what's that going to give us here, well, if we're taking in a limit as h goes to 0 from the left, f of h is going to be equal to negative h. What is the limit going to be as h approaches 0 from the left of negative h divided by h? Rachel?
Negative 1.
But if we plug in 0 for h, don't we get 0 over 0?
But since it's a limit.
Since we're taking a limit, we can do the old swoosh swoosh and get negative 1. Yeah, for h that's close to, but not equal to 0, we can do the old swoosh swoosh on this and get negative 1 is our answer. About, let's do from the right now. Because we saw that if we take our derivative limit as a limit as h approaches 0 from the left, the limit came out to negative 1. See what happens if h approaches 0 from the right. I think what's going to happen is first line is going to be the same. We'll get the limit as h goes to 0 from the right of f of h minus 0 over h. And what can we say about the absolute value of h, because f of h is absolute value here. What can we say about the absolute value of h if h is a positive number?
Positive h.
I think so. If your number is positive to start with, then the absolute value doesn't do anything. The absolute value of something positive is just that number again. So h. So we end up with the limit as h goes to 0 of h over h. Huh?
Okay, I might just be confused, but I don't see how, from the left, how that function is approaching -1.
How f of x is approaching -1?
Yeah, from the left,
Certainly looks like it's approaching 0, doesn't it?
yes.
I think it is. Which
So-
fortunately, when we take this, that's not what we're looking at. is we're looking at f prime of 0, which is not the same as f of x. So in other words, Ellen, I think what you're saying is it looks like the limit as x approaches 0 from the left of the original function f of x is going to be 0, which I would agree with. What we're actually looking at here, though, is going to be a limit sort of as x approaches 0 from the left of f prime of x, not f of x. So that while the y values are approaching 0 from the left, the slope is from the left is behaving like -1. Does that make sense? That's it. I think it's just you're just a little bit confused as to what this expression we're looking at actually tells us about the graph. What is the limit as h goes to 0 from the right of h over h, by the way? Please?
Just one.
I think we can do the old swoosh swoosh again, and it's going to give us a +1. So f prime of 0 as a limit, the limit from the left, this limit from the left is -1. This limit from the right is +1. So what is the two-sided limit going to be if we don't specify the direction from which h is approaching 0? Undefined? I agree. Zach, I think your original hunch was correct. Our derivative of the absolute value function at 0 does not exist. And we can actually say the reason is because the slope from the left is behaving like -1, the slope from the right is behaving like +1. But the slope from the right is going to be +1. And so the moral of the story is, whenever you're looking at the graph of a function, it's like if you're playing like a video game and you're playing as Mega Man or Sonic. Pointy things are bad. Meaning, anytime you're looking at a function that has a corner like this, it's generally the derivative is going to be undefined there because the slope from the left and the slope from the right are going to be different values. That's kind of what it means when you're looking at a corner of a function like this, is that slope from the left and the slope from the right aren't going to match, and so the derivative at that point will be undefined. I think that's a good place to call it for today. So when we come back on what is today, Monday? When we come back on Wednesday, we'll take a look at the rest of Standard 10 and talk about what are other ways in which a function can fail to be differentiable at a point, in which f prime cannot exist. And we'll look at a bunch of examples. So hope you all have a good rest of your day. I will see you all on Wednesday.
Oh, I don't know about running.